Assalamualaikum and good morning.
Morning, doctor.
Can you hear me?
Yes, sir.
Okay, so today's lecture, we're going to learn about the second compensator in the frequency domain, namely known as lag compensator. Okay, so please refer to slide number 39. Okay, on the lag compensator. So lag compensator is different from the gain compensator. Okay, last week we learned about gain adjustment. Okay, where we have to move the gain curve up and down. Okay, in order to achieve the gain objectives. Okay, as given in the spec design of the questions. And today we will see on the lag compensator, which is namely used to improve steady state error without affecting the transient response. So it is similar like PI controller, okay, for time domain. Okay, and the equivalent in frequency domain is known as a lag compensator. So with the both diagram, we can design the lag compensator, okay, where it will improve the static error constant, okay, which is known as Kp, Ka, and Kb, okay, by increasing only the low frequency gain, okay, where we increase the low frequency gain. It will also increase the phase margin, okay, to yield the desired transient response. So it will involve low frequency gain and it will involve a phase margin. So for that purpose, we must look at the structure of the lag compensator. So the lag compensator is can be represented by GC, okay, GC, which is C stands for compensator, equal to S plus 1 over T over S plus alpha T, okay, which can be simplified in the simple manner, which is this one, is much better. S plus over ZC plus 1 over S plus PC plus 1. So ZC is the zeros of the compensator. PC is the poles of the compensator. Bear in mind, this is very important. ZC is greater than PC. Okay, so the value of ZC must be greater than PC. For example, S over 10 plus 1. So divide by S over 1 plus 1. So this is known as the lag compensator. As long as the value of zero compensator is greater than the poles of the compensator. So the workload for the lag compensator, as we know that 1 over ZC plus 1, sorry, S. over S over PC plus 1. Okay, so this is the gain compensator. So ZC is here. Okay, so this is the corner frequency for the numerator of the compensator. Divide by S plus PC, which is the denominator, which is on this part, PC. Okay, PC. Okay, so let me draw you the hidden, okay, which is here. Okay, so you have a ZC, you have a PC, where ZC is greater than PC. Then this compensator, if we add each other, okay, in the board diagram, this is the first one, and this is the second one. When we add together the gain curve, 1 and 2, so it will give you the total, which is this one, the black one, okay? Okay, center. Okay. So this is the total. The bold line is the total between the gain curve 1 and gain curve 2. So similarly, for the phase diagram, phase board diagram, ZC is greater than PC. Okay, so the phase for the ZC is here. This is ZC, which is correspond to 45 degrees. Okay, so this is the lower frequency. This is the higher frequency. Okay, and ZC is the corner frequency. And then for the PC, okay, so for PC is here. So it will start from here. Okay, goes here. Then it goes here. That is S over PC plus 1, where the lower frequency is 0.1 PC, 1 decade before, and 10 PC is the high frequency, which is 1 decade after. Similar to the ZC as well. So the lower frequency is 1 decade before ZC, and the higher frequency is 1 decade after ZC. So the total between phase 1 and phase 2 is represented by the bold line as shown in the slide. This is for the phase diagram. So the effect of the lag compensator can be listed as here. The uncompensated system is unstable to achieve desired static error constant, okay, which is the K. Okay, Kp, Kb, and Ka. Okay, so the lag compensator reduce the high frequency gain while not changing the low frequency gain. Okay, so that is the effect. And the effect is to stabilize the system due to the static error constant, and then thus the low frequency gain of the system can be made high to yield a large KV, okay, without creating instability. Okay, so this is the diagram that I showed previously, okay, which is here. Okay, this is much better if you split. So I put it here again, the uncompensated system. And then by using a lag compensator, okay, it will give you the compensated system, which is the blue line, okay. And KV here is the velocity error constants, okay, where ESS is equal to 1 over KV, okay, and KV is the formula there, limit S to 0, okay, SGS, which is the open loop system. So this is for the gain in decibels, and this one is the phase in degree. So in order to perform a lag compensation, okay, the lag compensator, so we have the procedure, the steps to design. The first one is to obtain the value of K, which satisfy the steady state error, and plot the corresponding work load. So work load is given, okay? Work load is given in the test or in the exam questions. So you just use the given work load, okay? It's good for you to print the work load if you have a printer, okay? Print the work load figure, and then from there you can start to apply the steps of the lag compensator. And then find the gain crossover frequency, okay? Gain crossover frequency so that the desired phase margin is obtained, okay? So you have to find the gain crossover frequency, which is omega GM. Omega, the gain crossover frequency, omega GM, okay? So rate the gain of the uncompensated system at this frequency, okay? The compensated gain needed is the amount needed to change the compensated gain to 0 decibels, okay? So you have to calculate the amount in order to make the existing gain become 0 decibels. Hence, the higher frequency gain, ZC, for the compensator is 1 decade below the gain crossover frequency, meaning that 0.1 ZC. Okay. Then draw a minus 20 decibel decade slope backwards until it meets the 0 dB line. So this will give you the lower break frequency, which is the PC, okay, for the compensator. So we look at the examples, okay, the examples shown here. Given the system below, use the board diagram to design a lag compensator to yield a 10-fold improvement in steady state error over the gain compensator system while keeping the percentage overshoot at 9.5%. So we are using the same block diagram as in the gain adjustment, where we have a pre-amplifier, we have the power amplifier, we have the motor and load, and we have the integrator 1 over S. From these questions, overshoot 9.5% will give you zeta, and from the zeta, you will get the phase margin. Okay. 10-fold improvement, meaning that if the error is 1, okay, so the new ESS will be 1 over 10, which is 0.1, okay, which is reduced 10 times from the old steady state error. Okay, so overshoot 9.5% will give you 0.6 zeta, and 0.6 zeta will give you roughly 60 degrees phase margin. So you can use a graph given here. Okay, this graph is faster compared to the formula given. Okay, so this graph will be included in the exams so that by using this, so you can actually get the values. Okay, so 9.5 is about here, 0.6, and then 0.6 is about here, which is 60 degrees, something like that. Okay, so the gain K from the previous example is 583.92. So from example 3, overshoot 9.5%, the K is 583.9, okay, and KB is 16.22, okay. So 16.22 is you can get from the booklet or you can get from the calculation. KB is equal to limit S to 0, SGS. GS is the open loop. So the open loop will be the gain and the poles at the origin, poles at minus 36, and poles from the minus 100, which is from here. Okay. So the KV will be 16.22. So the desired KV is 10 improvement, okay, which is 116.22 multiplied by 10, so that you get 162.2. Okay, don't get me wrong, as I told you before, so the old one, ESL's old, is 1 over KV, which is 1 over 16.22. How much is it, the error? Telpel? 1 over 16.22.
Doctor, 16.22 or 162.
1 over 16.22.
0.06165.
0.06165.
0.6165.
lah.
Okay.
So then the new one will use the new KV, which is here. New KV, KV new, which is 162.2. Telpel again, ESS new, 1 over 162.2.
I got 6.16 times 10 by the power negative 3.
Negative 3, meaning that 0.00
616.
61. Okay. So you can see that the previous steady state error is 0.061 and the targeted is 0.0061, meaning that the error becomes smaller. Okay. You compare the old one and the new one. So now we are working on the new one. So therefore, the K also 583.9 is multiplied by 10, which is 5839, that to achieve 162.2. So we plot 5839, okay, into the board plot as shown here, okay. So this is the board plot for the before lag compensations, okay. So you can print this one, okay, so that you can play around to design the lag compensation. This is the phase one, okay. I draw it by axles. So before compensations, okay, when we plot these open loop transfer functions, so it will give you gain margin minus 1.53 decibels and phase margin minus 4.37 degrees. Okay. So in the lag compensations, what we will do is we will design the lag compensator, okay, where the high frequency is 0.98 and the low frequency is 0.062 with the slope which is 20 decibel per decade. Okay, so the targeted phase margin is here 1/110, which is 60 degrees. So the solution will be at 9.5% overshoots, will give you zeta 0.6 and will give you 59.2. So usually in order to do the lag compensator, we have to put a correction factor. Okay, we just add the 59.2 with 10 degrees. Okay, the correction factor. So student will ask, is it compulsory or not? So I advise you to add 10 degrees. Okay, because that is quite challenging when we do it in manually. Okay, by manually drawing. So that's why we cover the correction factor 10 degrees in order to avoid mismeasurement or wrong measurements. So it will become 69.2. Okay. So to make it easy, usually I assume this one 60 degrees and this one 70 degrees. So easy for you to calculate. So even though your answer is not same with your colleagues, with your peers, no worries. Okay, because we have a judgment, we have the tolerance of maximum and minimum in order to accept your compensator, lag compensator design. So at omega 9.8 radian per second, okay, 9.8 radian per second, which is roughly here, which give you the phase margin, okay, 60 degrees, 70 degrees, okay, which should give you 70 degrees. This one is for decimal where phase margin 70 degrees, okay. So we draw a lag compensator, which is 1 decade before, 0.98, okay. 9.8 is the frequency, the ZC, okay. And the high break frequency is 1 decade before is 0.98. And the low break frequency is 0.062 radian per second from the drawing, okay, roughly, okay, which is minus 20 decibel per decade slope line, okay. So the transfer function now will become, this one is your ZC, and this one is your PC, okay. You can see that the value of the compensator ZC 0.98 is bigger than 0.062. So as long as your ZC is bigger than PC, so your answer is correct. Okay. But if the student design the lag compensator 0.063, he get 0. Let's say 0.5, and the PC is S plus 5. Of course, the answer will wrong because the ZC is smaller than PC. So you have to make sure that the ZC is greater than PC. Okay. So the compensated system now will become 3.6786, the gain, plus the ZC, plus the zero poles at the origin, poles at minus 36, and poles at minus 100, plus the PC, which is 0.062. Okay, so the phase margin about 69 degrees or 70 degrees, which will give you 9.67 radian per second. So when we plot here, okay, the frequency, which is 9.68 radian per second, which will give you phase minus 110 degrees. So this will give you phase margin 70 degrees positive. Okay. So this is the final plot when you include the lag compensations, okay? So it will give you about 63.7, okay, roughly. If you don't add 10 degrees correction factor, this phase margin may be a little bit lower, okay? So that's why we play the 10 degrees correction factor, okay, in order to achieve that. This one is considered as acceptable design. Any question? So far, okay? Everybody okay? So tomorrow is the lockdown.
Are you okay, doctor?
Okay, okay, as usual. So no pressure on student, okay? Do your best, do your assignment, submit your assignment, okay? Okay, if there is no questions, we go to the example 4. So example 4 is the lag compensator, another examples of lag compensator. So for a unity feedback system with the forward transfer functions, which is G equal to K divided by S, S plus 50, S plus 120. So use both diagram to design a lag compensator for the system that will improve the steady state error tenfold again. Okay, tenfold, right? That is the 10 factor, while still operating with 20% overshoot. So use the previous K as 194, 200. Okay, so this is the answer. Okay, you can see that ZC 2.04, PC 0.141. So ZC is greater than PC. Always remember this in the lag compensator. So I give you the plot, okay, using Excel for you to print, okay. So this is the open loop transfer functions, 194,200 over S, S plus 50, S plus 120. All these examples are taken from Norman Nice book, okay. Norman Nice book, which is this book, okay. If you have difficulties to understand my slide, you can read this chapter 11, okay, book chapter from Norman Nice. So I take the examples from this chapter. So initial gain margin is 14.4 decibels, okay, and the phase margin is 48.1 degrees, right? So the overshoot is 20%, which will give you zeta 0.456, and the phase margin is 48.2. This is all taken from the standard graph here, which is the overshoot versus zeta and phase margin versus damping ratio. So the solutions for 20% overshoots for K194,200 and for KV 32.37, which can be calculated from the formula or can be get from the board plot, okay, KV. If you still remember, okay, so KV, how to find KV from the board diagram? We follow the theory that I showed you before, which is this one. This one, okay, see? So you take the ruler, okay, this is minus 20 dB per decade and it cut at 0 decibels. So this is your KB. So in this case, Okay, so in this case, this is a minus 20 dB per decade. So you just use a ruler, and where it cut is somewhere there, okay, at the 0 decibels. Yeah. So the value is 32.37. Okay. Both are you can get from the formula and you can get from the plotting. Two ways. Okay, 32.37. So for this one is the whole steady state error 1 over 32.37. Okay, so you get the value here. And this one is multiplied by 10. Okay, the KB multiplied by 10, so you will get 3 to 3.7. Of course, the new one, which is 1 over 3 to 3.7, which is smaller than the old one. So therefore, the K also have to be multiplied by 10. So 1942,000 to achieve this KB. Okay, so we plot. So at the end, this plot will be given. You don't have to plot, okay? They will give you this plot, okay? And you observe the value there, where the gain margin is minus 5.59 decibel. The phase margin is minus 15.7 degrees, which is unstable, okay? So we have to design the lag compensator where the desired overshoot is 20%, which will give you the zeta, which will give you the 48.2 degrees phase margin. So in order to compensate using a lag compensator, so we add correction factor. So this one you must follow, okay? Use it. Correction factor 10 degrees, so that our phase margin now is 58.2 degrees, the new one, the targeted one.
Doctor, is the correction factor always 10 degrees or?
Yes, we are following normalized book.
Okay.
Okay, so 10 degrees. So in order to achieve 58.2 degrees, so the frequency gain crossover frequency that will achieve that is 20.5 radian per second at magnitude 23.2 decibel. Okay, so we draw a lag compensator frequency, lag compensator hybrid frequency, which is 1 decade before 20.5. So this 20.5, 1 decade before is 2.05. Okay, radian per seconds. And then we draw the minus 20 dB decade slope line, okay, which is like this. Okay, this is the minus 20 dB slope line, so which will give you 0.141. And this one is 2.05. Okay. So the transfer function now has been changed, has been designed where ZC is 2.05, this one, and PC is 0.141. ZC is greater than PC. Okay, and the gain is 0.0691, which is the ratio between PC and ZC. Then you plot this one. Okay, you plot, then try to find the phase margin, which is 48 degrees, 58 degrees, which is 20.5. Okay, 20.5. This one is 58. It's not 48. Okay. Then the overall lag compensation is shown here, but the gain margin and the phase margin I didn't include here, so you can use this one, put in the MATLAB, and then you can search the value of phase margin, which will give you 58 degrees. Okay, at 20.5 radian per second. Right. Any questions so far? Okay, if there is no question, we move to the lead compensation, the last one. Okay, so in this chapter, focus on gain adjustment, lag compensator, and lead compensator. So lead lag can be ignored, okay, because the calculation solution is too long. So lead compensator is the third compensator, okay, to improve the transient response. So this one is equivalent to the PD controller. Okay. So with the both diagram, the lead compensator, okay, will increase the phase margin to reduce the overshoot percentage and increase the gain crossover frequency and bandwidth to realize a faster transient response. Okay, this is the impact of lead compensator. So the transfer function of lead compensator is given by 1 over beta, okay, S plus 1 over T divided by S plus 1 over beta T, where beta is less than 1. Please remember that. Okay, so it can be simplified as GC, which is a lead compensator, S plus S over ZC plus 1, divided by S plus PC plus 1, where ZC less than PC. Yeah, not similar like lag compensator, ZC greater than PC, but for lead compensator, ZC less than PC. And then beta actually is the ratio between ZC over PC. Mass less than 1. Okay, mass less than 1. So this is the two important methods in the structure of the compensator. Right, so GC is equal to 1 over ZC plus 1, S divided by PC plus 1, where ZC is less than PC. Okay, so we draw the ZC first, which is this one, ZC. Okay, for the gain curve. And then for the PC is shown here. This is the PC. Okay, so 1 decade before ZC is 0.1 ZC. 1 decade after ZC is 10 ZC, which is this is the low frequency and this is the high frequency. Similar to the PC as well, this is the low one and this is the high frequency. 1 decade before and 1 decade after. Then when you add together, okay, so it will give you the bold line, which is the total of the gain curve 1 and 2. Similar to the phase as well. Okay, so we wrote again 1 over ZC, S over 1 PC. Okay, so the ZC, which is here, this is the number one, and PC, which is here, okay, which is ZC is less than PC. So when you add 1 and 2 together, it will give you the bold line, okay, as the total of the phase curve. So the uncompensated system has a small phase margin, which is B. Yeah. Yeah, B. Okay. and a low phase margin frequency, which is A. So using the lead compensator, the gain crossover frequency is increased from A to C. Okay, increase from A to C. So this yield a larger phase margin D. Okay, a higher phase margin frequency C, and a larger bandwidth, which is BW. Okay, this is the impact of the lead compensator. So the board for the lead compensator depends on the beta value, where beta is equal to ZC divided by PC. And the value varies from 0.1, 0.2, 3, 4, and 5 for the gain, and 0.1, 0.2, 0.3, 0.4, and 0.5 for the phase curve. The peak and the phase curve vary in maximum angle at the frequency where the maximum occurs. So in lead compensation, they are using more formulas compared to the lag compensators. For lag compensators, you have to use Bode diagram, the given Bode diagram, in order to find the targeted phase margin frequency, the ZC and the PC. There is no way you can use the formula in lag compensator, but in lead compensator, you can use formulas. Okay, so the formulas are given here. The frequency at the maximum phase angle, which is omega max, ZC divided by square root beta. The maximum phase angle, which is phi max, is the inverse sine 1 minus beta divided by 1 plus beta. And then the compensator magnitude, omega max, okay, here is the magnitude GC, J omega max, which is equal to 1 over square root beta. Equation 1, equation 2, equation 3. No need to memorize due to given in the exam. Okay, you don't have to remember this formula. It's given in the exam. So similar to the lag compensation, for lead compensation also there is a step to design it. Okay, so step number 1 is to obtain the value for K which satisfy the steady state error, and then plot the corresponding Bode plot. So this is given. Okay. Find the phase margin of the uncompensated system. Then you have to use a correction factor as well. Calculate the additional phase needed by the lead compensator so that it satisfies the system requirement. So you need a correction factor 10 degrees to be at plus 10 degrees. Then calculate the beta value, which is ZC divided by PC. Continue to calculate the compensator magnitude to obtain the beta above. Then obtain the new gain crossover frequency, omega GM, subject to the magnitude of the uncompensated system, is equal but negative to the compensators. Hence, you will get the ZC and PC. ZC less than PC. Draw again the Bode diagram to check whether the spec design has been fulfilled. Okay. But if the spec design is not fulfilled, so you have to repeat again with the new correction factor. Either increase from 10 degrees or less than 10 degrees. Example 5. We are using the same block diagram. So given the system below, use the Bode diagram to design a lead compensator, which will give you 20% overshoot. KV is given as 40 with the peak time 0.1 second. Okay, so the open loop transfer function based on the board diagram is K 100. This is the open loop transfer function. So for KV is equal to 40, K is equal to 1440. Okay. For board plot, excuse me. Dia nak tabur baja. So dia masuk. So the board plot with the diagram, K is equal to 1440. So the desired overshoot will be 20% and phase margin is 48 degrees from the given standard curve. So from the GS, okay, the open loop transfer function, okay, so we use the phase margin formula or the graph, then we will get the 48.2 degrees and the KV is 40, okay. So I give you the board plot here. So if you use a ruler, okay, you can see that this one is minus 20 dB per decade, okay. So if you use a ruler, so you can see that the KV will cut over there. KV is equal to 40. I'm using a freehand draw, so you cannot get exact at 40. So you draw it, okay, and then you can see that the current system, the open loop current system is stable at gate margin 10.6 decibel and phase margin 34 degrees. So from the board diagram, you can see that phase margin 34 degrees at 29.6 radian. Therefore, the required phase margin is 48.1 degrees, which is the targeted, minus 34, which is from the measurement, from the board diagram, and then plus 10 degrees. So it will be 24.1 radian, 24.1 degrees at 37.1 radian per second. Okay, the targeted minus the given board plot phase margin 34 degrees plus 10 degrees. So that is the targeted 24.1 degrees for the lead compensator. Then you use the formula, okay, which is given here, formula 1, 2, and 3, okay, which is omega max 39.6, the frequency, so ZC divided by square root beta. So beta will give you 0.42, the beta, which is a 25.66, the ZC. The phase maximums is 24.1 degrees. Okay, this will give you beta. Suppose this one goes first. Okay, so that's why you get 0.42 over there. Okay, and then the magnitude will become 3.762, 3.76 decibels. Okay, which is 20 log 1.543. So this one goes first, this one goes to second, this one goes to the third one. How to use the formula. So by using the equations, so the maximums phase margin is 24.1 degrees with beta 0.42. And by using the lead compensator magnitude, you will get 3.76 decibel at omega maximum. So therefore, to select the new phase margin, we will use the omega max here, okay, which will give you the 3.76 decibels, and the board diagram at omega max is 39 radian per second. This is by doing drawing or for the lead compensator, but usually we use the formula is more than enough. Formula number 1, 2, and 3. So the ZC is 25.3 and PC is 60.2. So ZC is less than PC. The ratio is less than 1, which is 0.42. This is your lead compensator. So it makes sense because the ZC is less than PC. Then multiply with the current open loop transfer functions. Okay. Then you will get the spec design. Okay. Which is 45.5, the targeted, okay? 45.5 degrees, which is in the range of acceptable value. So I leave example 6 for you, more or less is about the same as example 5, okay? So the lecture has been end at 31st of May today, okay? Our syllabus is finished. Then starting next week, we will revise exams questions for 1 month from 1st of June until 30th of June before final exams. Is it okay, everybody?
Okay, Doctor.
Okay. So with that, I ended my lecture. Okay. No class for tomorrow, 12 p.m. No class tomorrow. Next week, we will go to the test 1, test 2, and final exam reviews. I will share the question later. Okay. Thank you very much for listening. See you next week. No class tomorrow. Okay, no class on Wednesday, sorry. Wednesday.
Isn't that also 4.5 for lead lag?
Sorry, league lag is not included in the exams.
Oh, not included.
So our scope for chapter, the final chapter is until page until page 93. 93. League lag is not included in the final exams.
So this page is from what book?
Norman Nice book.
Oh, Norman Nice.
Is given in the book chapter in the WhatsApp list. Okay. Okay, guys, thank you very much and see you next week for revisions from chapter 1, 2, 3, and 4, including assignment discussions. All right.
Okay.
So I hope assignment has shown some improvement. Please look at it. Okay, because the due date is 17th of June.
Thank you, Doctor.
Thank you.
Stay safe, Doctor.